Lava can reach 1,200 degrees Celsius, enough to melt the surface of a road, but not to vaporize a skyscraper overnight. Hollywood says buildings vanish in a wave of fire, yet concrete and steel tell a slower, stranger story. So why do cities sometimes withstand eruptions, only to fail from forces much less visible? The real threats may not be what you expect. Lava is more than just molten rock. It is a moving, evolving force with its own rules. At its hottest, lava can reach temperatures between 700 and 1,200 degrees Celsius. That is hot enough to turn asphalt into bubbling liquid and to set wood ablaze, but it does not mean instant destruction for everything in its path. The real story starts with how lava flows and changes as it moves. Basaltic lava, common in places like Hawaii, is known for its low viscosity, which means it can travel long distances before cooling. This type of lava forms two main surface textures, pahoehoe, which spreads out in smooth, ropey sheets, and ae, which breaks into jagged, clinking chunks. Both types start out searing hot, but as they flow, the surface cools quickly, forming a dark, solid crust. That crust acts like a blanket, trapping heat inside and slowing down the cooling of the molten core. Underneath, the lava stays hot and mobile, while the outside hardens enough for a person to walk on, if they dared. This insulating effect means that even as lava creeps forward, the heat does not always penetrate deeply or instantly destroy what is beneath. Instead, the process is one of gradual assault, surface charring, slow cracking, and, over time, the breakdown of materials exposed to relentless heat. Understanding these mechanics, temperature, viscosity, and the formation of an insulating crust sets the stage for why the reality of lava's impact is so different from the instant devastation seen in movies. Hollywood loves to turn lava into a villain that moves with impossible speed, swallowing skyscrapers in a matter of seconds. Films show glowing rivers racing down city streets, buildings collapsing in fiery explosions, and heroes outrunning walls of molten rock. The truth is far less dramatic, but much more interesting. Real lava flows are slow, often creeping along at less than 1 kilometer per hour. Structures do not simply vanish on contact. Instead, they face a long battle against heat and pressure. Instead of instant collapse, you get gradual charring, cracking, and sometimes even survival, at least for a while. This difference is not just about spectacle. It shapes how people think about volcanic danger and what they expect from real eruptions. In reality, the most dangerous threat to a building is not always the lava itself. Volcanic ash can pile up on a roof until the weight causes it to cave in. Wet ash can reach over 100 kilograms per square meter, turning rooftops into traps. So, which is actually more dangerous, lava or ash? The answer is not as obvious as the movies suggest. When the camera cuts away from the action, the real story is about slow, relentless forces, not sudden catastrophe. That is why understanding what actually happens during an eruption matters, and why the next step is to look at how these forces play out in the real world. In 79 AD, the city of Pompeii was buried not by rivers of lava, but by a cascade of ash and pumice from Mount Vesuvius. As the eruption intensified, roofs across the city buckled under the weight. Wet volcanic ash can load rooftops with over 100 kilograms per square meter, enough to bring down even sturdy timber. Archaeologists have found that while many stone walls remained upright, the roofs collapsed first, trapping everything beneath. The true killer was the combination of suffocating ash and the searing heat of pyroclastic surges, which reached temperatures between 250 and 600 degrees Celsius. Entire neighborhoods disappeared under 2 to 3 meters of debris, their structures preserved only because they were entombed so quickly. Fast forward to 1980, when Mount St. Helens erupted in Washington state. Here the story repeated itself on a modern scale. The lateral blast and ashfall destroyed over 200 houses and buried roads and railways. In the days that followed, heavy ash blanketed towns for miles. Wet ash accumulated on rooftops, sometimes exceeding 100 kilograms per square meter. Power lines snapped, and buildings that survived the initial blast suffered roof collapses, leaving homes and businesses uninhabitable. The timber industry lost 4 billion board feet, and the total damage reached $1.1 billion. A USGS volcanologist explains that it was not lava that devastated the region, it was the ash and the blast. Most buildings failed because of the sheer weight overhead, not from being burned away. These cases show that, time and again, ash, not lava, poses the greatest risk to buildings. The next question is whether big structures can survive when lava finally arrives, or if there are ways to steer disaster away. On the Icelandic island of Heimaey in 1973, a wall of lava crept toward the town and its only harbour, the community's lifeline. Rather than abandon hope, engineers led by Thorbjorn Sigurgeirsson set up massive pumps to spray seawater directly onto the advancing flow. More than 6 million tons of water were used each day, cooling the lava so rapidly that it hardened and slowed, forcing the molten front to change direction. The harbour was saved, and many buildings, though surrounded by black rock, remained standing. But a closer look revealed the cost. Some homes, even as their walls survived, had their foundations undercut by heat and shifting ground, leaving them unstable and unfit for living. A similar story played out in Hawaii during the 2018 Kilauea eruption. Homeowners watched from drones as lava oozed around their houses, sometimes stopping just meters away. For Ikaika Marzo in Leilani Estates, the sight was surreal. His home still upright, but the ground beneath scorched and eroded. Inspectors later found that the soil had been baked and swept away, rebar exposed and concrete cracked. The house looked untouched from above, but was condemned as unsafe, a shell left behind by the slow, grinding force of the eruption. These cases show that it is possible to steer or even outlast a lava flow, at least for a time. But survival is never simple. Structures that appear to have made it through may be weakened beyond repair, uninhabitable, even if they are still standing. Lava can be diverted, but its heat and weight leave scars that do not always show on the surface. Concrete and steel, the backbone of modern construction, face a harsh test when exposed to volcanic heat. Laboratory tests show that at 300 degrees Celsius, concrete begins to spool, meaning chunks break away explosively as trapped moisture turns to steam. Once temperatures reach 500 degrees Celsius, structural steel loses about half its strength. Engineers describe this point as a critical threshold. Above 500 degrees Celsius, steel softens rapidly, and it will not hold the loads it was designed for. The process isn't dramatic at first. Surface layers of concrete pop and crack, exposing the steel reinforcement inside. As the heat persists, the bond between concrete and rebar weakens, leading to slips and fractures. At 800 degrees Celsius, steel can lose up to 90% of its original strength, enough to cause beams to sag or collapse entirely. These failures do not always start with visible flames or explosions. They begin with silent, relentless weakening from the inside out. The true danger is not instant melting, but the steady loss of structural integrity as heat invades deeper with every passing minute. No structure can truly claim to be volcano-proof. Even the strongest concrete and steel face limits when exposed to the realities of an eruption. While some buildings survive the initial assault of heat and pressure, the damage doesn't end when the lava cools. Volcanic gases, especially sulfur dioxide, seep into cracks and pores, reacting with moisture to form acids. Over weeks and months, these acids corrode steel reinforcements and eat away at concrete, slowly undermining the very bones of a building. Acids can be silent, and the effects build over time. Engineers can design for brief encounters, with thicker concrete and special coatings, but these measures only delay the inevitable. Every eruption is different, and defenses that work in one place may fail in another. The slow attack of acidic gases often escapes notice until walls crumble or rebar turns brittle and rusted. Survivors of eruptions sometimes find their homes still standing, but chemically weakened from within. In the end, there is no universal design, only a series of compromises, each shaped by the unique chemistry and force of the volcano itself. Modern engineering can slow volcanic destruction, but nature still dictates the terms. As urban growth edges closer to active volcanoes, the real challenge isn't just surviving the lava, it's learning how to adapt before the next eruption rewrites the landscape. What would you change if you lived nearby?